Hi everyone. Welcome back to Dave's Math Channel. I'm your host David Tear, and today I'm going to do another calculus video. I haven't done one in a while. I thought I had completed my series on first year calculus, but I think I made an oversight by not discussing a very important method for approximating finding roots of differentiable functions. The method's called the Newton-Raphson method. I guess it was first developed by Isaac Newton, and I think it was improved a little bit by another mathematician named Raphson. But anyway, it's a very simple algorithm. It's kind of written in the middle of this slide. Um, I'll go over it though. Let's begin. So here's the idea of the method. We're trying to find the root of some nice differentiable function, which is kind of shown in black on the left. So we have some function f of x, and we want to estimate its root. I mean, the function might have more than one root. A root is just a zero. It's another name for zero. It's just a point where f of x equals zero. So we want to find some value of x such that f of x equals zero. That's what's known as a root. And we start with an initial guess. The way we do this is we start with a guess. Usually you start with x0. Here, I guess they're calling it x1. But anyway, so here they start with x1. And then, it has to be a reasonably good guess. I mean, it is sometimes this method doesn't converge. So you have to start with a guess that's sort of close to the actual root. It doesn't usually have to be that close, but it has to be sort of close. So I know that sounds vague. I mean, you can make this precise if you want, but I don't want to do that in this video. So we're starting with this initial guess x1, and then what we do is we compute both f of x1 and f prime of x1. And how does that help us? Well, f of x1 is just the value of y at x1. That's just the height of this point. You see the point on the left above x1 on f, that's f of x1. That should be 0 if we made a good initial guess. Here you can see it's pretty far from 0. But what can we do to get a better estimate? Well, we can assume that f has a constant slope. We can assume that f is linear. Yeah, of course it's not really linear, but we can make that assumption that it's approximately linear at least, and that it has the slope equal to the slope at x1. And if that's the case, then the function would look like this line going down with slope m equals y2 minus 1 over x2 minus x1. Probably learned that in high school. That's just the slope of a line with two given points. And so, we already know the slope. We just have to find the points. So we extend this red line, which is the tangent to our function, all the way to the y-axis or the x-axis, and we see where it intersects. Well, it intersects at this point x2 comma 0. So that gives us our second iteration. And in this case, for the example they show here, it's still not a very good estimate. I think it's a little better than the first estimate because we made a pretty bad first guess. That's why the second estimate is still pretty far. But, once this method starts converging, eventually it starts converging very, very fast. That's a nice thing about this method. So anyway, I mean, just let's keep going through this. So now we have the point x2. We do the same thing. We take another line. We compute, f of x2 this time is negative. It's closer to the x-axis than our first guess. And again, we find the tangent line and we see where it intersects the x-axis. This time it intersects at x3. And we keep going. So now we get our third guess, x3. You can see that x3 is better guess than x1. And by the way, this is pretty typical. Usually the iterations go back and forth. They don't always alternate around the true root, but sometimes they do. And I guess the example is showing here they do. When we do it a fourth time or third time, we get x4. This time x4 is really close to our curve. So, you know, and anyway, that's the idea of the Newton-Raphson method. Very powerful method. And here's just another example. I'm not going to go through this in detail. Here they do use x0 as the initial guess. And same idea, the function they're doing here looks kind of like a parabola. And Once you get close to the actual root, you keep getting closer and closer with successive iterations. So anyway, and now I'm just gonna give you some examples. So as a first example, let's use the Newton-Raphson method to estimate the square root of 2. I did another video recently where I estimated the square root of 2. I think I did one using Taylor's series. That's another way you can do this. I even did a video where we showed how I can do Taylor's series in my head, at least the first iteration, which usually gives you a estimate that's around 3 decimal place accuracy. So you can kind of impress your friends if you know how to do that. But anyway, here I'm not doing this in my head. I'm writing out the steps. So let's use Newton-Raphson here. And how can we use Newton-Raphson to estimate the square root of 2? Well, we first have to find a function that's a root of. Well, I think it's pretty easy to see. X squared equals 2, so if f of x equals x squared minus 2, then square root of 2 is a root. As a matter of fact, it's the unique positive root. Of course, there's another root, which is the negative root, minus the square root of 2. But we don't care about that root. As long as our initial guess is kind of close to the square root of 2, we're fine. So let's make a pretty good initial guess here. I think you guys know that square root of 2 is pretty close to 1.5. If you didn't know that, it's pretty easy to see because 1 squared is 1 and 2 squared is 4. So you want a number that's between 1 and 2, and 1.5 is halfway between. Anyway, so let's just start with x0 equals 1.5 and see what happens. Well, our first iteration, and you always have to compute the derivative of f, by the way. Before you even start this method, you should first compute the derivative of the function you're trying to find the root of, which in this case is x squared minus 2. And we all know how to compute the derivative of that function. It's just 2x. So f prime of x is 2x. So now we have all the information we need to apply the Newton-Raphson method. So let's just do it. X1 is x0 minus f of x0 over f prime of x0. F of x0 was 1.5. So f of 1.5, this is 1.5 squared minus 2. I'm writing it out in detail on the first step. And then the denominator is 2x0, which is 2 times 1.5. If you simplify things, the fraction turns out to be 0.25 over 3. And then if you do one more step, here I'm using decimals. You could actually use fractions and get an exact answer. But here I'm using decimals. And if you do this using decimals to 5 decimal place accuracy, you'll get x1 as approximately 1.41667. So that's our next estimate of square root of 2. It turns out to be a much better estimate. And let's do it one more time. So now let's do it again. Here the calculations get messy, but same idea. We apply the same formula. X1 now is 1.41667. So f of x1 is going to be 1.41667 quantity squared minus 2. And then the denominator is 2 times x1, which is 2 times 1.41667. One thing I think you'll notice when you apply this method, the numerator keeps getting smaller and smaller, which is good because that means you're converging on the root. So now the numerator of this fraction turns out to be just minus 0.0, what I get here? 0.069539. It's pretty small. And then the denominator is a lot bigger, 2.83334. The denominator doesn't typically get small, but the numerator does. And when you simplify this, you get 1.41667 minus 0.00245. And if you compute that, you get 1.41422. Well, that turns out to be really, really accurate because the actual answer is approximately 1.41421. So we got it within about 1 part in 100,000 just by doing 2 iterations and just by starting with a pretty crude guess. So this is a pretty powerful method. But just remember, you usually have to make a pretty good first guess. As a matter of fact, if we started with a guess 1, this method wouldn't even converge. I don't think it would converge for the guess 2 either. So you have to make a reasonably good guess. Let's do another example. This is kind of an interesting example, I guess. I think. So here we want to find the unique root of the function x minus cosine x, which is also known as the fixed point of cosine x. It turns out that the cosine function, and we're using radians as the argument, by the way, but it turns out that the cosine function has a unique root, a unique fixed point. That means there's a unique value of x such that x is equal to cosine x, where x is in radians. And let's try to find what that root is. So we start with f of x equals x minus cosine x. We want to find the value of x that's there such that x minus cosine x equals 0, which is just another way of saying x equals cosine x. We have to start with a guess. Let's just start with a guess 1. Kind of pick this out of thin air. Probably a better idea to graph the function to get a better idea where the root is. But it's pretty close to 1, right? I mean, it's not that close. But if you start with that x0 equals 1, this method will converge. It's not as good a first guess as for example 1. But let's just see what happens when we apply this. So do the same thing. X1 is x0 minus f of x0 over f prime of x0. This time f of x0 is 1. F of x is x minus cosine x. X0 here is 1. So the denominator is 1 minus cosine 1. And then the derivative of x minus cosine x is 1 plus sine x. So the denominator is going to be 1 plus sine 1. And when we plug in the numbers, I'm not going to go through all the steps here, but when we plug in the numbers and simplify, we get approximately 0.75036. That's a better estimate. That's a much better estimate than 1. But let's just apply this method one more time to get an even better estimate. So let's do it a second time. Now we just do the same thing. We plug in x1. So now we have to start x2 is x1 minus f of x1 over f prime of x1. Again, we just apply the formulas. F of x1 is going to be x1 minus cosine x1. And f prime of x1 is 1 plus sine of x1. And we know what x1 is. It's 0.75036. So when we plug in that value of x1 and simplify, this time we get approximately 0.73989. That's pretty good. It's not great. It's not nearly as good as our last example. The actual answer turns out to be about 0.739085. So we got it right up to the third decimal place, but it's farther off than our last example. But it's still a pretty good estimate. It's within about 1 part in 1,000. So, even though we started with kind of a bad first guess, after just 2 iterations, we get a result that's pretty close to the right answer. So, as you can see, this is a pretty powerful method. If we kept going, we'd get closer and closer very fast. So, anyway, let me just do one more example. How about trying to calculate the natural logarithm of 2? And now, x, so we let x equal log 2. That's what we want to try to find. And now we know that e to the x is 2, since the e to the x is the inverse of natural logarithm. Saying x is long ln 2 is just the same thing as saying e to the x equals 2. That means e to the x minus 2 equals 0. So if you let f of x be e to the x minus 2, we're just trying to find the root of f of x. I think that does have a unique root. And the derivative is very easy to compute. The derivative of e to the x is e to the x. Derivative of 2 is 0, so the derivative of f of x in this case is just e to the x. So now let's apply this method. Let's start with a guess x0 equals 1. That's a pretty bad guess, but let's just start with that. It turns out it does work if we start with x0 equals 1. Uh, if you wanted to get a better estimate, you should start with a better first guess. But let's just see what happens when we do this. So again, we apply Newton-Raphson method. X1 is x0 minus f of x0 over f prime of x0. And f of x0 is going to be e to the x0 minus 2. And f prime of x0 is just e to the x0. And if you plug in the numbers, you get, I'm not going to go through all the steps, but if you plug in the numbers and simplify, you get 0.73576. That turns out to be a much better estimate of the natural logarithm of 2 than 1, but it's still not a very good estimate. So let's do it one more time. If we apply a second iteration, I'm not going to go through all the steps, just do the same thing. I guess you'll notice that the numerator of the fraction is now getting pretty small. The previous iteration was pretty big, 0.71828. This time it's 0.08707. And when we simplify everything, we get 0.69404. Well, that's not a bad estimate. It's not a great one. The actual value was 0.69315. It's actually a pretty good estimate. It's about 1 part in 1,000. Off by, well, 1 part in 1,000. It's incorrect in the third decimal place, but it's only off by 1 in the third decimal place. So it's really a pretty good estimate. I'd say it's about as good as our last example. So we didn't have to do too much work to estimate the natural logarithm of 2, and you can keep going. You'll get a better and better estimate. Anyway, that's the Newton-Raphson method, and that concludes my video. Thank you for watching. Long live math, and I'll see you guys next time. Bye.